up mga ka-axis? In this video, I'll be discussing the homogeneous transformation matrix of a Cartesian manipulator. When dealing with rotation matrices, we can merge 3x3 rotation matrices by multiplying them. However, this isn't the case with position vectors. Multiplying position vectors isn't feasible due to their dimensions, while it's possible to add them. It's not the correct approach for combining position vectors. This is because position vectors represents translations, which include both distance and displacement. Adding position vectors could result in incorrect distances that would hinder the performance of our mechanical manipulator. To properly combine position vectors with rotation matrices, we use something called a homogeneous transformation matrix, often denoted as H or T. These matrices are commonly used in robotics to handle such transformations, but in our discussion, we will use H. Just like a rotation matrix and a position vector, a homogeneous transformation matrix uses superscripts and subscripts to indicate the reference frame and the frame being described. Essentially, it's a 4x4 matrix that combines a 3x3 rotation matrix with a 3x1 position vector. This combination allows us to describe both rotation and translation in one unified framework, which is particularly useful in robotics and 3D modeling. A homogeneous transformation matrix is a mathematical construct used in robotics and computer graphics to represent the position and orientation of an object in space. It combines rotation and translation into a single 4x4, allowing for efficient computations and transformations of points or objects within a coordinate system. The general form of a homogeneous transformation matrix T is like this. Then, where R is a 3x3 rotation matrix representing the orientation of the object, D is a 3x1 translation vector representing the position of the object, and 0 is a 1x3 zero vector. The bottom right element is always 1, which allows for the matrix to be invertible and used in various transformations. A homogeneous transformation matrix is a tool that captures both a rotation and the position of a mechanical arm. It includes a rotation matrix and a position vector within it. It effectively combines these matrices similar to how we combine rotation matrices. They must be square. A square matrix has an equal number of rows and columns. So, to transform a 3x4 matrix into a square 4x4 matrix, we add an extra column known as an augmentation column or the 001 column. The augmentation column, which is made up of numbers 0001, transform our homogeneous transformation matrix into a 4x4 matrix. This column also acts as a scaling factor, affecting how our 3D object appears in terms of distance when its orientation and position change. The homogeneous transformation matrix originates from the transformation of a mechanical manipulator from one frame to another. It combines the rotation matrix, which describes the rotation from one frame to another, with the position vector, which describes the translation of the original frame to the new one, resulting in a unified 4x4 matrix. This matrix can be used to perform operations such as rotating, translating, or scaling objects in a three-dimensional space, and it is particularly useful in the context of robotics, manipulators, and computer graphics modeling. Computing the homogeneous transformation matrices of a Cartesian manipulator in robotics involves representing the position and orientation of the manipulator in a compact matrix form. Here's a general approach on how to calculate the transformation matrix. First, get the rotation matrices 3 by 3 of each of the joints of the manipulator and insert it in the homogeneous matrix in the upper left side. Because our manipulator is a Cartesian, we don't have any rotational joints, so we will multiply it by stationary matrix or the identity matrix. Then, step 2. Obtain the position vectors 3 by 1 of each of the joints of the manipulator and insert it in the homogeneous matrix in the upper right side. Let's get the position vector of P01. In this part, let us get the position vector of frame 1 relative to frame 0. The distance between the origin of frame 1 and frame 0 along x sub 0 axis, because frame 0 is the reference frame, is 0. Why 0? Because along x-axis there is no assigned link length, as well as the y-element, because along y-axis there is no assigned link length. Then for the z-element, there is a link length along the z-axis, so the z-element is a sub 1. Then this apply to all the position vectors until complete. For step 3, insert the augmentation column to make it a square matrix. Step 4. Let's do it for all of the joints of our Cartesian manipulator. Get the rotation matrices and position vectors of the joints. So this is the homogeneous transformation matrix of H01. This is the homogeneous transformation matrix of H12. This is the homogeneous transformation matrix of H23. And this is the homogeneous transformation matrix of H34. So, why should we do this? The homogeneous transformation matrix is key in robotics because it contains all the information about mechanical arms, rotation, and position. It's like a master plan or blueprint that guides the design of a robot arm, detailing on just how it rotates and where it's positioned, but also the length of its segments and how it will move. In essence, this matrix is what engineers and designers aim to create when they're building a new robotic arm. That's all for this video. I hope you understand the homogeneous transformation matrix of a Cartesian manipulator. And I'll see you on our next video.